First, an announcement that next week's colloquium is on bacterial motility, swimming or gliding, question mark. And that'll be given by Howard Berg of Harvard. Now to the main event. It's my distinct pleasure to introduce today's speaker, Reinhard Genzel. Reinhard is one of the directors at the Max Planck Institute for Extraterrestrial Physics in Garching, and is also officially now a POG here at Berkeley, a professor of the graduate school. As some of you may know, Reinhard came to Berkeley in 1980 as a Miller postdoctoral fellow to work with Charlie Townes, and some of that history Reinhard will describe a bit today. He then stayed on as a faculty member in the early 1980s. In 1986, he was lured back to Germany, to Max Planck, as a director at MPE. Fortunately, he's maintained an affiliation with Berkeley since then, and typically comes to visit for several months each year. I think if you took a poll of many in the astrophysics community and asked them who had been the highest impact astronomers in the last 30, 35 years, Reinhard's name would be on or near the top of many of those lists. And I think the reasons for that are really threefold. One is what we'll hear about today. It's the seminal contributions to establishing the case for a black hole at the center of the Milky Way that really is far and away now the best case we have for a black hole in astrophysics. The second reason is that Reinhard has done equally important and influential work on understanding how galaxies form and evolve, how the universe went from the smooth initial conditions at the Big Bang to the dizzying variety of structure that we see around us today in the form of galaxies like our own Milky Way, galaxies that aren't forming stars today, etc. And then third, and I think probably most importantly, it's the methodological approach that he takes. Reinhard combines a great scientific acumen with a real facility for instrumentation. And the group that he's developed at MPA is really unique in their development of cutting-edge instruments to do the science that they want to do. This includes instruments for space-based missions and also ground-based missions. And some of what we'll hear about today in the form of the gravity interferometer on the VLT, Reinhard has described to me as the hardest experiment that he's ever worked on. His many contributions have been awarded by a large number of prizes. I'll just mention two. One is the Crawford Prize of the Swedish Academy, and the other is the Shaw Prize in 2008. So with that, I'll turn it over to Reinhard.
Thank you very much. It's an absolute pleasure to be back and to see so many familiar faces. Some of us, like me, are getting a little old and weak in the knees and so forth, but it's still fun to do science. And today is, for me, a particular pleasure, I must say. Elliot has described to you how I came to Berkeley, and having then the chance to work with Charles Townes, who had come here from the East Coast just about 10 years earlier, or 15 years earlier than that, and to work on a number of subjects. And his work, when I was a student, was legendary. And you know, if you went to the fifth floor Burge library of Charlie's, you would see all these theses stacked up there. And every one of them was a revolution. Every one, every single one. So I'll talk about two such revolutions today, a little bit in retrospect, but then also to show you that one of the things you have to do in science sometimes is to be patient and work hard. Charlie would approve of that. You have to work hard. So the issue, ostensibly what I'll report to you today, is in fact the first work ever done with infrared interferometry on the center of the Milky Way. And I'll tell you how we will use that in the next years to very plausibly be able to detect a number of the effects of general relativity on an object of 4 million times the mass of the sun. But then as we as we do this and see how hard it was to get there, of course it's nice to be nostalgic and see how this all came about. So this is where the historic part comes in. So put your minds, if you can, about a half a centennial ago. For some of you that's not possible. But then, in fact, a number of things happened which are important to the story I will tell you about. For one thing, 50 years ago, the so-called quasars were discovered. That was because the radio astronomers, in fact, then were capable for the first time with their interferometric antennas to pinpoint the sources of radio emission and count them and see where they were, and then told the optical astronomers about some of them. And in fact, one such object which you see on that image, 3C273, discovered in Cambridge, was then looked at by Martin Schmidt with Palomar. And a spectrum in the optical showed that the redshift of these objects was, for that time, huge, 17%. And that was huge, because at that time, the universe, as seen by the astronomers, was rather modest. So this implied, if you believe that redshift to be cosmological, a huge distance of several million, 100 million light years, which was hard to believe. And then, if you then took the light, which you see here, of a 13th magnitude star and converted this into an amount of luminosity or energy, that turned out to be about 1,000 times the radiation of the sun. Of the Milky Way. So a very luminous object, yet very compact, which you can see by seeing basically the diffraction spikes. Looks like a star, a quasi-radio star, quasar. So then the theorists went ahead and tried to explain that with various things. I want to make the story short. And within I would say about a decade, it became clear that the most plausible way to generate this much energy was with a black hole, which seems at first paradoxical, because after all, black holes are supposed to be black, right? Or green or something like this, but I mean, certainly not radiating much, and yet here they were generating so much energy. Of course, the trick is that this blackness only occurs within the so-called event horizon, and the event horizon is a very small volume in space, whilst outside of this, there's gravity still at work in its normal ways, and you can generate energy by having accretion of material onto this black hole and through various electromagnetic processes then generate hot gas disks, accretion disks, as in this picture here, which are outside the event horizon and produce this enormous amount of energy. In the process also spewing out relativistic particles along the poles, fast plasma jets. So this picture, which took hold in the late 60s, and you see some of the famous names associated with that, Donald Lindenbell, Lord Rees, and Rashid Tsarnaev, and many others, really sort of made that massive black hole paradigm, as we call it, very plausible as an explanation for these most massive and most luminous objects called quasars. But then you would like to really get close to these objects, and that's where the problem comes in experimentally. These things are so damn far away that if you wanted to prove this, you would have to measure, of course, the gravitational potential. Gravitational potential you can measure, if you think of the solar system, if you have test particles, for instance, planets, or stars, or gas, which are at different distances from the object. And if Kepler's laws are right, well then, as you go to the center, the motions increase like 1/√R. That's true in general relativity as well. And so if you measure this, then you can measure the mass of the central object, and you can perhaps measure how compact it is and show that it must be a black hole. So the principle, how you might want to do that, it was pretty obvious. In fact, Lindenbell and Rees published a very influential paper in '71 saying basically, look, this is how you do it. Now, we appreciate you can't do that in quasars, but principally, if there are such black holes out there, here and there, maybe these are just the active ones, and there are others which are not active, and they could be the centers of all galaxies, like, for instance, our own. It's remarkable how seminal and foresightful that remark was, because that's what it has turned out to be since that time. And that was sort of the marching order for Charlie and me and many others over the years to try to prove this. At the same time, roughly speaking, another thing happened, which was that Roy Kerr, a New Zealander, published what is the most important metric in GR. There's a third one. The Schwarzschild metric is without spin, but the Kerr metric is the description of space-time with spin, which is the one which is likely going to be realized in astrophysics. And it is interesting to talk to Roy, and then those people who were obviously just using the Schwarzschild throat, they didn't call it black hole back then, as a sort of a conceptual way to explain quasars. They didn't talk to each other. Very interesting. I mean, the GR world was really a mathematical exercise of a small community, which had nothing to do with the astrophysics community, who are just getting to this point. But that actually happened at the same time. So also, of course, at the same time, that was the time when Charlie Townes got his Nobel Prize back east for the invention of the maser and the laser, and then short story, he then decided, he didn't want to continue in that anymore. He wanted to do something new, and he came back here in 1967, started a new group, and that group was turned completely away from the laser, more or less, and towards astrophysics, and that's what we pick up a little later. So the Galactic Center really, in that sense, is perhaps of interest because you're a particular fan of our own Milky Way. For me, the Galactic Center is a laboratory, and so it was for Townes. It is one because it's the closest such system. So what you see here is in infrared light, in a modern picture, the Milky Way in the center. So we're talking about the central few hundred light years in this image. And the Galactic Center is well hidden in the visible from our eyes by about 30 magnitudes. You cannot see it. You have to go to the infrared. And at a few micrometers, you begin to see here this very strong concentration of stars, but you still see these clouds of interstellar dust and gas. And it's this concentration of stars, of course, where you might expect something to happen. And so Lyndon Bell and Rees in the 71 paper said, why don't you go ahead and look there? And so the radio astronomers did, and so Charlie Townes did. The radio astronomers at that time were getting pretty good in terms of making images in the centimeter range. This is the green-colored emission from thermal, mostly of thermal radiation, plasma, protons, electrons. But then there is where you see this cross, this asterisk here in the central now. We are now on a scale of 1 parsec, so we're reduced by a factor of 100 compared to the most recent picture. Here is obviously sort of streams of gas, and then in the center of this there seems to be a very compact radio source, which the people discovering it called Sagittarius A star. Science is always associated with people, so I want to, from time to time, enlighten this talk by showing you some of the people who were associated with that. Ron Eakers and Fred Lowe, who just passed away a year ago. So the radio emission clearly showed that there was activity in the center of this sea of dense stellar light, which you see here in blue and reddish colors. So Charlie, of course, then told his students, we've got to build an instrument. Of course, in a wavelength range which nobody had worked in because it's extremely hard, at 10 micrometers where they have a lot of background radiation. There were hardly any detectors sensitive at the time, but he did it. Tom Jabal and Eric Woolman and John Lacey were the first ones to build a Fabry-Pro spectrometer to look at the emission of the neon-2 fine structure line at 12.8 microns. And here from the Woolman paper are some spectra. They're much more beautiful spectra, of course, nowadays, but I want to show you that even then you could see the effect of the black hole right there. Namely, when they placed the apertures of their measurements in different places along this radio mini spiral near SgrA star, you could see that the central apertures have very wide lines and with very different central velocities. And the Doppler velocities you derive from this are hundreds of kilometers per second. So if you take gm over r or v squared r over g, you immediately see there must be a large mass there, no doubt. And in fact, you get an order of magnitude right without much model building. So that is what, over the years, from the late 70s into the 80s, kept the Townes group busy, and the evidence for this mass concentration became ever more obvious. It became also clear it was not stellar, it couldn't be a bunch of stars. It had to be, Townes was convinced already in 1982, it must be a black hole. And there must be exactly that kind of a proof, if you like, of the Lynden-Bell and Rees scenario. Well, as you will see, it's not quite as easy as that, because on that scale here, there's still a number of other possibilities. In principle, you could think about clusters of neutron stars, et cetera, et cetera. So in order to exclude these, actually took, I'm afraid to say, 3 decades. So this is the patience part. And we also did work hard. And the scenario went south, mainly because the Galactic Center is south. And the facilities here you see are the Paranal facilities of the European Southern Observatory. That and the Keck are our best current optical infrared telescopes on the ground, and the VLT arguably is now beginning to really show off its strength as the leading facility. You see, there are on the site at 2,600 meters in the Atacama Desert 4 8-meter class telescopes. These are these things. In addition, you see these little ones, 2-meter class telescopes, which can be moved around. They might play also a role in the interferometry, however not in the story, which I will tell you, because we need these giants, as you will see later on. So it's the story of using this facility for me and my group to build instrumentation which allowed us to make ever sharper imagery in the near infrared and spectroscopy also in the near infrared, in order to basically move ever closer to the center and make the statement we can make about the mass concentration ever more significant. And that has a lot to do with adaptive optics. The scintillations refraction of the Earth's atmosphere is well known in the optical to, of course, make the wavefronts from distant objects which are initially flat crumpled. So if you image that, then you get flickering seeing, which limits the resolution to about a half an arc second. And that's not good enough to measure over time the motion of an object, just because the flicker smear is so large. So what you need to do is you have to undo what the Earth atmosphere does. Of course, you can send this telescope into space, and the Hubble telescope has done a little bit of work in the field, but in the end, it's the size of these objects, these telescopes, which you really want to exploit. The size, meaning the diffraction limit of these telescopes, is much better than the Hubble. So that's why you would like to make the wavefronts flat. One does this nowadays in a technique where you have either a star or an artificial laser beacon star near the object of interest. And then you basically observe the wavefront from the laser or from that nearby star, analyze it, have a deformable mirror, and then basically flatten the wavefront, and thereby correcting for the Earth atmosphere. That does work pretty well. It's not perfect. Nowadays, routinely, in particular with laser guide stars. And so our group has been involved in a series of ever more ambitious instruments, initially for one of the individual telescopes, UT4, with the first diffraction-limited imager, NACO, then a so-called integral field spectrometer, Symphony, then the first laser guide star we developed for ESO, and then the most recent thing, which you'll hear about, is to actually then use all 4 telescopes together as a gigantic, not 8-meter, but 130-meter diameter telescope. So that's sort of been the story. The first decade of this 3 decades saw us and a second group at UCLA, led by Andrea Guess and Eric Becklin and Mark Morris, develop sharp, deep imagery of the center in the near infrared with this kind of technology which I've described to you, and then went ahead patiently to wait until gravity would move the stars from one year to the next, and after a few years you began to see the motions. It took about 3-4 years to believe it, then another year or two for the other group to confirm it, and then we could do things like this. We're now in the central half-arc second, so that's very high resolution. That's a light month now. You see the images of stars in 3 different years. Red is the first year, green is the second year, blue is the third year. And you see their SgrA star, this green cross, and you see the 3 years positions are clearly separate. There's no doubt. And if you look up here, there's a little calibrator. That's 2,000 kilometers per second. So that's obviously, you know, about 100 times or almost 100 times the speed of the Earth around the Sun. Again, you can take v squared r over g and get a first order calibration of how much mass you need, and you find it's the same 3 million solar masses which Charlie had done 10 years earlier, okay? Now, however, on a scale of less than a light month. And you also see that as you go out away from SgrA star, the prism effects become less. The velocities go lower. That's basically a qualitative way of expressing. There's a Kepler law at work, which has a concentrated mass. And so you can plot that more quantitatively, velocity dispersion as a function of radius from SgrA star. And you see here there is this Keplerian tail going up to several hundred kilometers per second near SgrA star to a lower value out, and then a mass which is in here of a few million solar masses. So that was the first decade. But we weren't happy because, again, as I said, on that scale you could still introduce a number of other possible explanations of what the nature, the physical nature of that central mass might be. And so to prove that it must be a black hole, you have to go as close as possible to the event horizon. And so how you would do that is not so clear. You have to be lucky. And nature, in this case, played along, which you cannot always, of course, dictate, and gave us stars which are on planetary scales, down to about 15, 20 light hours away from the black hole. So the second decade, continuing into the third, saw the two groups observing ever more not velocities, but actual orbits, including one complete orbit, which we saw for the first time coming around around SgrA star here in 2002. And so then went back out, two groups here in blue and red, measuring pretty much the same thing, and then coming back in. And of course, the reason I stand in front of you is that they're coming back. And so that's the opportunity here when coming back, when coming so close to the center of 15 light hours, where you might hope to see GR effects. That was clear already 10 years ago. So that's why, in fact, already 10 years ago, we began developing new instrumentation, which then would have to have much higher angular resolution. Here we are talking about the precision of measuring the stellar positions to about a milliarc second or half a milliarc second. But we had to do at least 50 times better in order to see the GR effects. That was clear. So that's the story which you will see. Now let's turn to Sagittarius A star, that radio source at the very center. So the radio astronomers used very long baseline techniques, Earth scale aperture baselines, to show that this central source is extremely compact. Its size varies with wavelength, but I don't want to mention that in detail. When you go to the shortest wavelength, which is near 1 millimeter, the current available, but soon to be updated numbers show this so-called visibility plot here, which tells you that the source has a size around 20 micro-arcseconds in radius. So that's about twice as large or so than the event horizon radius of a black hole of a few million solar masses. So one must be very close here to the true high curvature radius of the region. Now there's no image yet. It might happen later this year, in fact, but we don't quite have an image. It might look something like this. And the reason you see sort of a half-moon shape is that, of course, the effects of special relativity by themselves already Doppler boost or deboost the radiation, depending on whether the electrons which make that synchrotron radiation come at you or go away from you. So there would not be an equal illumination of, say, a screen. You would always see a sort of a distorted signal. Then come, in addition, the GR effects, which at a few Schwarzschild radii are enormous. Now, interestingly enough, when you look at the spectral energy distribution of SgrA star, its peak is in the radio millimeter region, and then it sort of softly drops off into the infrared and X-rays in the so-called normal state or soft weak state. There is no strong emission in the near-infrared into the optical, which would indicate the presence of a very hot accretion disk, as in quasars. Apparently, and that's another part of this story, the accretion onto such black holes is much more complicated than thought in the 1960s. In fact, Elliott worked on this problem, and slowly people are now beginning to understand that there is sort of a bright state of a black hole with an accretion disk, and this advective state where basically the electrons and the protons are sucked into the black hole but not produce a lot of radiation here in the optical. X-rays, yes, infrared, yes, and then a lot of millimeter radiation, but no thermal bump. Now sometimes you see something very special, and so while monitoring the stars, all of a sudden we noticed an object which looked like a star on some of the images, but we knew from the spectroscopic evidence was actually also an ionized cloud. And here you see the velocities of that cloud versus the position relative to SgrA star as a function of time. So we started seeing it retrospectively in our data actually in 2004. Then it moved up, getting closer, and then beginning to be distorted ever longer. At one point then it was at the maximum and then already on the other side, like a spaghetti, like a textbook case of a spaghetti tidal distortions of a gas cloud. That was very exciting because a star, unless it gets very close to the black hole, sort of does okay. It has to follow the GR space-time, but it doesn't get distorted all that much unless it really gets tidally disrupted. Whilst that gas cloud just doesn't have any other choice. So we knew when we started discovering this that this was a way, an experiment, to actually test how much gas there was inside. Because in addition to gravity, that gas cloud sees also the hot plasma around the black hole. And we expected from the numbers at that time that we would see a lot of disturbance of that gas cloud right after Perry. And the answer is we haven't. So there's much less in there than we would have thought, okay, by currently we think about a factor of 100 in density. So that was you could call it a big mistake, but you could also say, wow, you learn something in science from time to time. So the status of this work after 3 decades is then as follows. We can measure the mass of the central object to about 1–2%. The main arrow is the distance to the galactic center, which we also measure, by the way, geometrically in this, about a few percent uncertainty. But the main uncertainty is the mass, is the distance, and this is basically the arrow ellipse, a combined, marginalized of all the uncertainties, and as you see, 4 million solar masses. And if you plot the mass distribution as a function of radius logarithmically, from the outer parts where the stars dominate, to the inner parts where there's one mass only, which is SgrA star, always 4 million solar masses. To the innermost point, we currently have a star. down to the event horizon where we have the radio and infrared size limits. All of this is a fairly simple region dominated by this one object, which is fairly quiescent, not at all like a quasar. It radiates at a level of about 10 nanoquasars, okay, which is another surprise, I should say, but I don't want to discuss. And so in this region, if you like, it's mostly empty, excepting theoretical models indicating a number of long-lived stellar product things, like for instance stellar black holes. There will be about 100 or so stellar black holes in this innermost region. Neutron stars, there should be thousands of neutron stars. We have only seen one at this point, unfortunately, because a neutron star in its form as a radio pulsar would be extremely valuable as a clock in the Einsteinian sense, but we haven't been given that by nature quite yet, maybe to come. But everything else is totally dominated by this central point, which, if GR is applicable, is a black hole beyond any reasonable doubt. So that's what Elliot said. Until the discovery of LIGO 1.5 years ago of the 30 solar mass inspirals, this was the best case of any black hole, and it's still the best case for a massive black hole. But of course now the inspiral, I would say, has overtaken that in terms of telling us that the space-time of the 30 solar mass inspirals indeed is what we would have expected. Okay, now let's return to Charlie in the meantime. Here he was, and those who know him will hear him, and he says, "My approach to science can be compared with that of an exploring naturalist. I'm curious. I like to explore things, and I like to push limits. New instrumentation capable of making measurements never available before can always be expected to reveal new phenomena. For instance, I look forward to examine objects in the Galactic Center with a mid-infrared interferometer." So that was Charlie in 1980. He really wanted to use interferometry because of the resolution, of course. So he knew that, and he worked on that, and in fact, he was the first one in the field to build an interferometer, which I come to. But for the benefit of those of you who are less familiar with spatial interferometry, let me just remind you of some of the principles. Basically, think of a distant star which you're observing with two telescopes. And the distant star then produces a flat wavefront which moves towards the telescopes, and let the two telescopes be separated by a distance b, and so as you see here, this wavefront at wavelength lambda travels down here. So then if you interfere the light from these two telescopes, if you like in a two-slit experiment like Young or Michelson experiment, then you basically interfere this two light, and you do this only in a positive interference if the optical path length difference delta here is null in the interferometer. So you have to inject as much extra path lengths in order to find the fringe, the positive interference. So the interference in this simple adding interferometer is just a cosine, which varies proportional to the baseline length, of course the sine phi, and b over lambda. So that's basically the fringe pattern of an interferometer. That's the principle. So that basically then allows you to get fringes on top of the resolutions of the two telescopes, which are here the envelopes. And obviously, if you displace these two telescopes by a large b over lambda, you get very fine fringes. And they allow you, of course, in principle, to go to very high resolution. So that's the first step. But now you would like to have an image. So here come the radio astronomers and realize that when you have a telescope like this, that as seen from the distant star, the baseline will move due to the rotation of the Earth atmosphere, due to the rotation of the Earth. So T1, T2, T3, T4, 4 different times, and the baseline has rotated. And that means that you get different components of the projection of those fringes on the sky. And in fact, you can then plot this in this way, where you plot in the x-coordinate, east-west, bx over lambda as u and by over lambda as v, and then such a baseline looks like a truck. Because the overall function is Hermitian, you'll see it's symmetric in this plane. And so then you get a UV truck along which the visibilities will change. Now, Martin Ryle in Cambridge knew about the van Sittert-Zernike theorem, which basically says that in the far field, the brightness distribution on the sky is the Fourier transform of the distribution of complex fringe visibilities, which you measure here on the sky with different baselines. So if you manage to cover all the fringe visibilities, all the baseline orientations and lengths, then you can fully recover the image on the sky at some resolution. So that's called Earth rotation aperture synthesis, and was put into fruition by the radio astronomers in the 1960s and led to a Nobel Prize, as you see here. Now, as you see, with one baseline, that's going to be very difficult because you don't have very much coverage. Let's take more than one baseline. Here you get a little more. Well, that's going to be sort of a cruddy image. And that's one of the troubles of the interferometry, that unless you have many, many telescopes, your image initially will always look cruddy due to the incomplete coverage in the UV plane. So for instance, if you take 4 telescopes like the ESO VLTI, and you make this measurement, and here you see these UV tracks on a given object, then that's how your beam will look like. There's a nice central part, which is milli-arcsecond diameter, but then there's lots of side lobes. So the tricks of the experiments I'll tell you about in the end for imaging is going to be how we deal with these side lobes, and actually how complex the images really are going to be, because otherwise we fool ourselves. So that was the radio astronomy in the 1960s and 70s, pretty well worked out methodology. Then Jack Welch here in Berkeley worked it out for the millimeter. But what about the infrared? Can we just go ahead and do this in the infrared? And Charlie said, of course we can. Well, there are some problems. The first problem is any path length difference or phase difference scales like delta nu over nu, where delta nu is the bandwidth of the objects you want to look at. So if you have a small bandwidth, basically monochromatic measurements, then it's very easy to get a fringe. But if you have wide bandwidth, it's very difficult to get a fringe. Likewise, if you have a given baseline B, the smaller the wavelengths there is, the harder it is to measure these phases, and also the motion of the phases. So if you go at that in detail, then of course you go from the radio to the far infrared, and everything gets more difficult by a factor of 100 or so. And if you go to the near infrared, where we work, as you will see, is another factor of 30 more difficult. If you want to work broadband in order to get sensitive work, your coherence lengths become nanometers or tens of nanometers. Phase-sensitive amplification becomes impossible or highly noisy. And that's a critical thing, because the way the radio astronomy technology works is you take one baseline at a time. So you take that baseline, that telescope with that telescope, measure the fringe visibility, and you make it that, and so forth. But you don't do this one after the other. You do it simultaneously by splitting the light and amplifying it again, so that you can make that measurement on all the different combinations at the same time. That works in the radio because we have amplifiers. But as you go to short wavelength, all amplifiers are quantum limited and produce very noisy results in the mid-infrared and the infrared. And finally, the atmosphere is not very pleasant to us either. The radio astronomers have a coherence time of the atmosphere of seconds to minutes. In the optical, it's 1 millisecond. So you can see how technology becomes so much more difficult as you go from the radio to the infrared. So that's, if you conceptualize this, you might see how, I would say, absolutely astounding it was that Townes took on this project in the 1960s and 70s. Because, I mean, how would you ever do this? His trick was lasers and narrow bandwidth operation. Because if you have lasers, and so he worked at 10 microns and he knew that there were CO2 lasers, then you would have a very phased, constant clock or a local oscillator with which you could establish the phase and then basically lock the different baselines too, and then you could mix heterodyne the radiation from one mixer to another with these lasers and get signals which you could amplify. The disadvantage is delta nu is small, so the sensitivity of these systems, unfortunately, are not as high as one wanted, and over time they have gotten better, but not stunningly so. Nevertheless, the final three-element interstellar infrared stellar interferometer, which Townes put up on Mount Wilson, was a great success, a really seminal contribution to the field of stellar dust envelopes and stellar sizes and so forth, which Charlie kept busy with his team, and Ed Vishnu and Walt Fiddleson are here until the very, very end, with baselines up to about 100 meters, so that's clearly been very, very successful. Unfortunately, Charlie knew this is not good enough for the Galactic Center, by about a factor of 10,000, I'm afraid. And so when I told him around 2005, we're going to try it in the near-infrared, he should have looked at me. You go ahead. And indeed, this was, as you will see, a hard ride, because we had to improve on all fronts. The first one is you have to have various comparisons. One is you have to have adaptive optics in order to make the wavefronts flat on each telescope. So you have, for 4 telescopes, that means you have 4 adaptive optics systems you have to manufacture. And in the Galactic Center, there is no visible star around, so you have to do this in the infrared. Well, to see adaptive optics, you have to make basically measurements of the pupil plane of the telescopes, very split up into many different pupils on so-called Schack-Hartmann sensors, and do this within the coherence time of the atmosphere on the star which nature has given us. That gives you a millisecond to detect it. Turns out none of the detectors when we started were good enough. In the end, there was a development which ESO, our institute, and a British company, SELEX, together did to develop a photo avalanche imaging detector in the near-infrared, or based on mercurium-cadmium telluride, which could achieve 1 electron read noise at a kilohertz, and thereby make the system sensitive enough that you could phase the telescopes. So now you have phased the telescopes. The next one, you need to make a phased reference observation, because you can never detect the fringes well enough within the coherence time on an object which is faint enough, like SgrA star. SgrA star is some varying, as you will see, between 15th and 19th magnitude. And the best you can do with these detectors is about 10th magnitude. So you need to have a nearby star which you can bring into the system, which you can detect the fringes on, and then use that as a phase reference to integrate the other system. So you have actually, for each telescope, 2 beams going in. And now the next thing is you have to operate on these beams. You have to combine the beams, you have to center them, you have to worry about misalignments and tip-tilt correction, all kinds of stuff, which you traditionally do on a big table in bulk optics. That would fill several tables here. No good. We say we will make a radical change here. We go all the way into a small door where there is a very good thermal environment, no vibrations, and go into single mode fibers. And so do everything in a combination of single mode fibers. Prior to this, you have to compensate for the geometric path lengths, which is done by ESO actually in a tunnel system underneath the 4 telescopes, which is 200 meters long, in order to compensate for the geometric delays. So we only, in the instrument, have to deal with the residual delays, and those we deal with in the fibers. So for each telescope, we make a 20-meter coil of fluoride glass fibers, which we stretch, depending where the reference tells us we should go. So we always are centered in phase with our science object. Finally, we combine the light of the 4 telescopes times 2 into the final combinations on an integrated optics chip. It's about this big in silica, where like in a radio waveguide almost, basically do all the combinations. So 4 telescopes in make 24 out in the end. And those you bring through a spectrometer and a polarimeter out to another one of those detectors, which has no noise. So that thing took us 10 years to build. And to make you enjoy what the poor photon has to go through in the last millisecond, I have a little movie, and I won't comment on it. I can, but let me just show it to you. What happens as we go from the Galactic Center, the last few hundred kilometers per second, into the central region. So there's the beam, Earth, hitting Atacama, hitting the first telescope. This is primary, secondary, going back down to tertiary, going now into a set of mirrors which brings the light down into the Coude focus of that particular telescope, where we now go into the adaptive optics train in order to correct the phase fronts on this. This is the adaptive optics bench there. With this low noise detector. Then the ley line tunnel brings the beams from all the 4 telescopes together in a laboratory here. In this laboratory we have our door, so the light comes in, free optics at this point, but now enters the door and will be manipulated there. There's a, acquisition system there, there's a field, there's a pupil optics system, and then in the end it's fed into single mode fibers, one for the science and one for the tracking reference. We can also correct images here, etc., etc. There's a K mirror in there. These are all perhaps details. But now we are really going from open optics into fibers, as you will see in a second. There we go. And so we now hit the first bundle of fibers for the residual optical path length compensation. There's that coil of 20 meters, which we can stretch on short time scales. Then we hit another coil system where we can actually squeeze the fibers to manipulate the polarization. And then the fibers, 4 for the science object and 4 for the phase reference now will be brought into the integrated optics, which will happen just now in a second. They go through a V-groove assembly out of the single mode fibers into the integrated optics right there. Now come all the multiplications, phase shifting, etc., come out, go through a spectrometer, grism, etc., and finally onto the detector, death of photon. Okay, so that's gravity. And so what we get out in our measurement is so-called fringe visibilities and phases for all the combinations of the telescope. So what I show you here is just one of the measurements now on the combination of S2, which is that star, which is to Perry next year in summer, and Sagittarius A star. Now, about Sagittarius A star, we know that it is fluctuating a lot. So in the measurements we so far have, we only see it some of the time. As you will see, that has now apparently changed. And the first thing we were astounded by is how complex the phases and visibilities are. That tells you that the field we're looking at is enormously complex. Now, the field we're looking at is constrained by the diffraction of the telescopes and the pickup fiber, so that in fact can be tuned to contain both SgrA star and S2. So that's what we do. So we use that double star, if you like, as sort of a lineup for our experiment. And we take many such measurements. We were busy all summer with 5, 6 big campaigns, a lot of traveling to Chile. Our PI, Frank Eisenhower, who is a genius as far as I'm concerned, must have had 1 million miles down to Chile and back this year alone. And then in the end, we do what the radio astronomers do. We have a UV plane filled with visibilities, and then we try to basically invert it to make images. Okay, so back into the science. What have we achieved? There is that field of stars around the black hole, which we've observed for 3 decades, with a good adaptive optics image of the present generation. There is SgrA star down there. That's the star S2, and this is the orbit which you've seen earlier. Little orbit here, 16-year orbit, on a scale of about 10 to the 4 Schwarzschild radii Apo and 10 to the 3 Schwarzschild radii in Peri. So we are now, in fact, a year before the thing will come around to its next meeting SgrA star, 1670 light hours away from the black hole, where we want to be ready. But in fact, it turns out it is essential to measure both before and after Peri in order to null out, if you like, the Keplerian part of the orbit. So this year, we've gone from these kind of images to that image. So that's an interferometric image, meets Sagittarius A star at milliarc-second resolution. There it is. And S2 here, that's the star at 14th magnitude. Here is an object at 18th magnitude. And so we've done this all year long. And so initially, we, of course, we are trying to compare different techniques. Our adaptive optics imaging experiment still goes on, just to make sure that we're doing the right thing. Whilst the new technique, the gravity measurements are coming in. They are the gravity measurements. We didn't always have good weather, but I mean, the results are very, very nice when the quality is good. And in fact, when we used to have to wait a month to see the motion, we see it now per night. So the object, the star, currently moves about 150 microarc-seconds per night. And we do see that, as you see. There's, still a little bit too noisy residuals. We need to understand that, but clearly we have already now achieved the 100 microarc-second orbital precision for the experiment. So what can we do with that? So there's 2 effects of genuine GR, which we hope to see. One is the gravitational redshift, and one is the Schwarzschild term of the Schwarzschild precession. They're all of the same order of magnitude of 1 over c squared. The gravitational redshift is, the residual redshift is about 100 to 150 kilometers per second, and the residual Schwarzschild term is 0.2 degrees for that star. So it's not easy to do, actually, on that particular star. So how well are we doing? Here is what our measurements this year, spectroscopically, as we come up on the predicted GR curve. And I mean, we are pretty hopeful that next year, perhaps even next spring, we have it. Okay, pretty good accuracy. The UCLA group is doing the same thing, I'm sure, and I'm sure also they will get a good result. So by next summer, that gravitational redshift should be nailed, or something is wrong. The precession is harder. There's the predicted residual. So here's what we did this year, obviously much better than what we had done before. by factors of 5 to 8. And so if we forecast this, it'll take us to about 2019 to see this kink in the orbit, which is really the precession. And because of the highly elliptical orbit, it's not a sort of smooth precession. What it does is basically a kink in the orbit. So we are fairly sure we'll be able to do that. Now there are other things we want to do, and a lot to do with the fact right around our SgrA star. Here is a distribution of the flux densities of SgrA star as we knew it before gravity. And you can see that the Sagittarius A star source is fluctuating from very high fluxes, very rarely to most of the time faint fluxes. So we were used to that, we knew that. With gravity, we were astonished to see how this goes on into those small flux levels. Here is a record of what we measured this year. And it goes up and down and up and down and up and down. And in fact, on what is a log normal distribution to the faintest levels, 19th magnitude we can achieve. That's very important because it tells us that there are, in the spectral power density, there is a lot of power coming in around 10, 15 minutes. That's about a half a Schwarzschild radius. So we are clearly down there with our measurements near the event horizon. Okay? We are down there. We are looking at regions near the event horizon as we think. And if we do, we might see the dynamics of the region. If we do, if we are lucky, if we have a situation where we have a bright spot which is moving, we might be able to see that. Whether we will see it or not next year, I would say we'll have to tell. But we haven't quite seen it yet. So at the present situation, we have outdone the specs. We thought we could go to maybe 16 or 17, but we're already doing regularly 18 to 19, which is improving the sensitivity of the interferometry by 7 magnitudes, factor of 600. And so we are doing Charlie's dream, I think we are. Now, you would like me to say something about the structure. Is SgrA star extended? Is there a third source? Because if there's a third source, there might be a star closer to than S2, which might allow us to get the next terms of GR. I will not say anything about this today because this is actually a fairly difficult experiment. Why? You've seen it. SgrA star is varying like gangbusters. Earth rotation aperture synthesis inversion is based on the stationarity of the image. You have to be able to Fourier transform. And that is, you have to have a stable source. When the sources are varying around, that's not given, and so the inversion is not clear. Now, the reason the source is varying is in part because its polarization is changing. So that we have to worry about too. We have not yet, although we are polarization sensitive. And finally, the spectral index of the emission may also change, which is a third variable. So we need to get these 3 variables under control in order to do a believable conversion. We think we think we see some structure, but before we talk about it, we need to make sure that it's not artificial due to the complexity of the time structure of the Sagittarius A star emission. So that is the status as of now. If indeed we can go on, we could potentially see the lens steering term, so the spin of the black hole, if we have a star which is about 5 to 10 times further in than S2. Instrumentation-wise, that seems to be no problem if it's there. The radio astronomers right now, this year, have started the so-called event horizon experiment, which I mentioned is to resolve really truly an image of the 1 millimeter emission. They have taken data. It'll probably take to the end of the year to see what they have. If one has a very strong prior prediction, since we know what the mass is, and the GR prediction is very strong and does not depend on spin, what that shadow size is. So if we measure that, in fact, from their work and our mass, we have an indirect test of the no-hair theorem. One has to see how well that works. And then finally, if indeed we can go to the dynamics of the gas around SgrA star, we might actually measure the metric on few Schwarzschild radii, but that requires the imaging progress which has been done. And then finally, of course, there's gravitational wave. The problem is we will have to wait about 10,000 years or so until the next star has the unfortunate in-spiral to be tidally disrupted. So that's a little too long, perhaps. So we have to then use other black hole systems. So here is our team, and happy after a decade of work to be able to focus inward bound to the black hole in the Galactic Center. And I'm very sure if Charlie would be sitting here, he would like it too. Thank you. So if you have it turns out that these innermost stars are almost on a perfect isotropic thermal distribution. In such a distribution, the high ellipticity orbits are very favored. So that's the first thing. Many of these orbits are highly elliptical. And then once you have an elliptical orbit in 3D, which I project for you in 2D, you can have all kinds of nasty things happening. So you have an ellipse like this, where we all agree when we look on it that this is the major axis and the focus is right there. Now if I tip it and you just look at the projection, there will be a point and all of a sudden your perceived major axis will flip from that axis to that axis. And then you will say, whoa, how can the focus be off the major axis? That's the effect.
When I used to observe it today, we used to say we didn't observe, we ignored, because we only detected about one in every 300 photons. How much ignoring do you do?
About 1%.
Oh, you're better than us.
Yeah, well, we do have better mirrors and so forth. And the fact that the end parts, of course, are not dusty, they're in a door, they're fibers and so forth, that helps. But you're absolutely right. These first 40 mirrors or so through the Coudet train, we could do without them, yeah. But
yeah, you mentioned that some of your short timescale variability might be due to polarization. Have you thought about observing in spectral polarization something that makes less sensitive?
it's mostly linear.
Right, but so the source is linear. So if you observe the circular, you'll be less sensitive to time and variation.
Yeah, no, but the optics is all.
But wouldn't that just be a quarter wave like in the line?
Well, we do have that, but I mean, there is so much instrumental linear polarization in the system because of the reflections. So much that yes, you can make, so to speak, you can make the residual instrumental polarization in the instrument circular, but you're still dealing with a background of huge, of apparent linear polarization, which is due to the entire train of optics in front of you. Potentially, yes. No, that's on our list. Look, will you understand? I mean, at this point, we're trying to get the raw interferometry to the level of sensitivity, etc. We've done that. Now comes the imaging, and then we'll come to the polarization and spectroscopy, so to speak, next.
You mentioned that the visibility looked very complicated even for just two sources. Is there any evidence for extended structure or more sources in that field?
No comment. Thank you for asking.
What are the guide stars used for grading?
What?
What are the guide stars that we use for grading?
Okay, so the adaptive optics guide star is a supergiant, 5 arcseconds away. Just a bright infrared object in the center of the system. So we are very lucky in that respect that we have such a bright system so close. In the optical, that would be hopeless. I mean, you cannot do this in the optical.
All right, let's thank Reinhard.
But it's a different topic. Very good. I'm going to go. There's a talk by a scientist. He founded a clock. It's like with physics and it's like kind of.
Yeah, well, okay, I'll bring it up. I'll bring it up with.
He's not like he's talking about